Alright, hello and welcome to another video of the MSU Denver video walkthrough of the Elementary Accuplacer Study Guide. In this video we're going to be talking about simplifying algebraic expressions, and simplifying is usually pretty easy, but in this case these problems they're actually kind of difficult, and to show you that even though it might not look like you can simplify, you actually can a lot of the times. If you're following along in the book, we are on page 26, and so I'm just going to run through just a few things. I'm going to do the odd problems in this section, in particular 1, 3, 5, and 7. I'm not going to go over 9 and 10 because 9 and 10 require us to factor like I haven't factored yet in these videos. There is a video in a few videos, if you want to go to that, a distribution and factoring video, where you're going to be talking about factoring those kinds of expressions. If you want to go over 9 and 10, if you're comfortable factoring like that, by all means, please do that. Check your answers in the back of the book. But since I haven't gone over it in those videos yet, I don't want to go out of any order. So I'm just going to be doing 1, 3, 5, and 7. If you go over 9 and 10, you get them right, great. If you're stuck on them, then please come into the tutoring center. We can go over that. But if you're on 9 and 10, or you want to do 9 and 10, you're like, I want to do every problem, then I would encourage you, if you're getting stuck on them, to watch the factoring video, not the factoring basics, but the other factoring video first. Get familiar with that, and then come back and try those two problems, because those two problems are actually really fun to do once you know how to factor. But before we get into these practice problems, I want to go over a few things about exponents. That's what we're going to be dealing a lot with in this section with these example problems, and then also fractions that involve variables, and in particular I'm looking at number 7 and number 5, but we'll get there. As far as the fractions, we'll go there, we'll walk through it. It's just like regular fractions. There are a few wrenches that they throw at you, but we'll walk through that. But just a few rules that I have gone over in other videos, but maybe you're skipping to this one because it's a tough section and you skipped all the other videos, and that's fine. But just to kind of reiterate a few things about exponents before we jump in, is that if I have something like a, let's say, squared, and I multiply by, say, a cubed, then I can add those, because these are both a, whether they're a or x or y or numbers. You can do it with like 3 squared times 3 cubed. If I multiply them, I add their exponents together, right? So this becomes a to the 5th. And why that works out? Well, a times a, right, which is a squared, and I'm timesing that by a times a times a, and so then I have 5 a's, and that becomes a to the 5th. So that makes sense. Even if I have something like a to the 4th, and I multiply by, say, a, well, maybe to the negative 2, right? Then that's I add them together still, so 4 plus a negative 2, so that's just the same thing as 4 minus 2, so that'd be a squared. And so if I multiply two things with the same base of, say, a, and I add their exponents together, then if I have a to the 5th and I divide that by, say, a cubed, then it should intuitively, we should intuitively think that, well, if I'm dividing them, I probably subtract the exponents, and that's in fact correct. So that would be 5 minus 3 is a squared, and that makes sense if we do this. If we write out a times a times a times a, I should have written fewer a's, but 5 a's, and then I have 3 here, and then I can kind of cancel them out, right? And they become 1s, 1 for the top, 1 for the bottom, and I do that until I run out on either side, and then what I have left is, on top I have 1 times a, so that's just a squared. Over, I just have 1s on the bottom, so over 1, which is just a squared, and that's what we have. And so a lot of you may be familiar with that, and that's good. But what if, and this is really what I wanted to kind of get to, what if I have like a cubed over a to the 5th? Well, the same rule applies, right? I should be able to subtract the exponents, right? And 3 minus 5, right, because I'm subtracting the exponents, would be a to the 3 minus 5, that's negative 2, right? And yet, if I write it out like I did up here, then on top I have a times a times a, and then on the bottom I have 5 a's, and then when I cancel those out and they become 1s, then what I'm left with is, on the top I have 1 times 1, so 1, and then on the bottom I have 1 times a, so a squared, right? And so in this way I get 1 over a squared, and in this way I get a to negative 2. And so what I want to go over is that the fact that those are two different notations for the same thing. Those are equal to each other, right? And so you probably won't see something like this, but if I have something like 3x to the, I don't know, negative 5, and and over, let's say just 5. I could rewrite that as 3. I'm not doing anything with the 3 over. I'm not doing anything with the 5, so the 5 stays where it is. I move the variable down, so x, and then I can change the sign. It doesn't necessarily become positive. If it's negative, it becomes positive, but if I wanted to and there was a positive exponent, I could move it to the bottom and make it negative. I don't know why I would do that, but I could. And so you just change the sign, and if I have something on the bottom, I can move it up to the top, so this would be to the 5th, but I could move that variable if I had 3x, if I had 3 over 5x to the 5th, I could do the same thing. Kind of undo what I just did and move the x to the 5th up and call that 3x to the negative 5 over 5. And that actually we will do a lot. I mean, not in these videos, but in calculus and stuff like that, that actually helps to do that. But you can go backwards and forwards, and you just change the sign on the exponent when you move it. And so if I look at the a to the negative 2, well, I could say that's 1 times a to the negative 2 because that doesn't change anything. I could divide that by 1 too because that doesn't change anything. And now I'm moving this a to the bottom so that I have a 1 left on top, and really I have a 1 on the bottom. I'm not going to, because 1 times anything is itself, so I don't have to write that. So I just write the a, and then I change the sign on the exponent so it becomes a positive 2, right? And so typically how you're going to see it, especially in these videos, is like this. And you're going to change that into 1 over a squared. But if there were like coefficients in front of it, the coefficients were just the same. It's just that the coefficients for the a to the negative 2 here, the coefficients are just 1. So times 1 divided by 1. So that's what that all looks like. And then one more thing that it's probably a lot of people probably know, but if you don't, we're just going to go over it real quick. If I have something like a squared and then I raise that to say the 3rd power, that's when I multiply these two, right? So a to the 2 times 3 is 6th. Even if I have something like a to the, let's say 1/2, and I raise that to the, let's say 2nd power, well here 1/2 times 2 is just 1, so this becomes just a. So that's nice. But why that works is that really what exponents are saying is I'm multiplying whatever's in here times itself this many times, right, for that particular exponent, the 3 out there. And so I can say that this is the same thing as a squared times a squared times a squared. And based on that, based on writing it out like that, and then using the rule that we used above, I could say, well, 2 plus 2 is 4 plus 2 is 6, and it would be a to the 6th. So it's just a shortcut just to multiply the two together. So having gone over all that, let's work through these problems, and let's start with number 1. And number one says, in parentheses, a squared times a to the 5th power, end parentheses, times a to the negative 12, and then I'm adding that, plus, in parentheses, a divided by a to the 3rd power. And so I'm going to work through a little bit on the left and then a little bit on the right, and we'll keep going. But on the left, in parentheses first, right, if I have a squared and I multiply by a to the 5th, based on what we just said before, this becomes a to the 7th power times a to the negative 12. And then this is plus. And then over here, I'm going to rewrite this as a divided by, and write it like that, the division bar, and then a to the 3rd power, just like that. And it's the same thing. I'm just rewriting it. And then if I keep working, on the left I have a to the 7th power times a to the negative 12. So I can add those together, and 7 plus negative 12, that's 7 minus 12. This would be a to the negative 5 plus, and then I could say that that's a to the 1, and since I'm dividing again, I could say 1 minus 3, so that'd be a to the negative 2. And honestly, in upper division mathematics, you usually, I mean, you're not going to see this kind of problem in upper division, but if you had negative exponents, typically we just leave it like that. But for this test, we don't like negative exponents. And so instead, I'm going to, based on the rules that I talked about before, I'm going to rewrite these as, that's the same thing as, I can say it's 1 over a to the positive 5 plus 1 over a squared. And that's a good answer too, but now that we have fractions, we're like, oh, because we have them, we have to combine them. We have to simplify it. And so the easiest way, I'm actually going to rewrite this right over here. 1 over a to the 5th plus 1 over a squared. If you didn't watch the video on fractions, typically it's easiest just to multiply the two denominators together, especially when you have variables. But since these are the same, if these were like numbers or whether or the same variables, I asked myself, can I make this, the smaller one, look like this? And in fact, I can, right? Based on the rules that we have above, if I multiply this one, it's not always easiest to see this, but if I multiply this by a to the third power, well, then I have a squared times a to the third power, and again, I add those since they're both a, and that becomes a to the fifth, and that looks like that denominator. And so I would multiply the top by a cubed based on the rules that we have to, do. And then this becomes 1 over a to the fifth plus a cubed over a to the fifth. And then since I have a common denominator, I can say, well, that's the same thing as 1 plus a cubed all over my single common denominator of a to the fifth. And what I just did there is equivalent to seeing a least common denominator. However, just like I talked about in the fractions video, if I don't see a least common denominator, even if there's one available to us, if I don't see it, I can always multiply the two denominators by each other. It's just that later on, if that's not the least common denominator, I'll have to reduce. And so let me show you what happens if I don't see that I can multiply by a cubed, right? And so I have this up here, and I don't see that I can multiply the right one by a cubed, the denominator of the right one. And so instead I'm going to multiply them by each other, and so I multiply this side by a squared, I multiply the top by a squared, and then I multiply this one by a to the fifth, and I multiply the top by a to the fifth. And then what I get is a squared times 1 is a squared all over, and then our common denominator is a squared times a to the fifth would be a to the seventh, plus a to the fifth over a to the seventh. And then I have a common denominator, and so I can combine that to say that's a squared plus a to the fifth over a to the seventh. And in the previous video, or previous couple of videos, I'm not sure which one, we talked about factoring out stuff, the basics. And if we look at the top, we can factor out something. And again, I said that the only reason you want to factor out something is if you can simplify, and that's what we're going to do, or solve for something. And so if I factor out, and what can I factor out at the top? Well, I can factor out, there's a to the fifth here, there's a squared here, and so I can factor out a squared. And then what I have left, remember I divide each term by what I factored out, so I have a 1. A lot of people, I ask you sometimes, what do you have left, right? And a lot of people say, oh, I factored out a squared, so what I have left is 0. But that's not true, and that's where dividing by what you factored out comes in handy, because if I have an a squared and I divide by a squared, I actually have a 1 left, right? So if I pull out everything of a term, what I have left is 1, not 0. And that's just important, and you'll definitely be able to see that when you try to distribute back through. It won't come out correctly if you have a 0 there. But I have a 1, and then a to the fifth, and I divide by a squared. Then I have a cubed left, okay? And then my denominator is still the same, a to the seventh. And now I have a squared times something, and I divide by a to the seventh. So I can cancel some of these out, and in fact, I can cancel both of the a's up top and 2 of the a's on the bottom. And so when I simplify that, and that's the reason I factored something out, I have 1 plus a cubed over a to the fifth power, which is the same thing that we have over here. Again, I said that if you multiply the two denominators by each other and it's not your least common denominator, you can still do that. It's just you'll have to simplify later. You'll have to reduce later, and that's what we're doing right here. We had to reduce. And so if you can't see that multiplying it by a to the third gives you a to the fifth, and that's your least common denominator. Don't spend too much time fretting over that. You just multiply the two numbers by each other. But it is a little bit harder because then you're going to get, after you get to this step here, you do have to simplify that. That's not an acceptable final answer. And so, but I mean, if you see you have a's everywhere, you should kind of think, well, maybe I can kind of simplify that a little bit. If I have a's all over the top and all over the bottom. And in fact, does simplify to 1 plus a cubed over a to the fifth. And so that's our final answer for number 1. That took a little bit, but we went over a lot in that one. And in particular, there's 2 ways to kind of do the last step. And so I wanted to make sure you saw both ways. And so we're going to move on to number 3 now. I'm going to skip number 2. I'm doing the odd problems up to 7. So number 3, let me draw a little boundary right here. Number 3 says, in parentheses, x squared y cubed z to the 0. And as you're writing down, if you're like, oh, z to the 0, that's 1, you can absolutely just write it as 1 or not write it at all because it's 1 times something. And that's all to the negative third power. and I'm multiplying that, because the parentheses are right next to each other, by x squared y to the 1. And if you want to just write that as y, you can. I like to write it as y to the 1 when I have to simplify a bunch of stuff like this, because it makes it'll help later on, as we'll see. But if you want to write it as just as simply y, you can do that. And then z cubed, and then we're raising all that to the positive 3 power. Now, you could take this whole term right here and say 1 over, and then make that a positive 3 on the outside, this 3 a positive. And you can absolutely do that, and then you're kind of dividing the two by each other. I'm not going to do that. It will work out the same. But the first thing we want to do is, if we talk about PEMDAS in parentheses, right, and I look inside this parentheses over here, I can't, because an x, a y, and a z, I don't know what they are. I can't multiply by each other, so we're kind of done inside the parentheses, right? But I have this exponent out here. And so, and this works, what I'm about to do, works when there's no plus or minuses or anything that's spread out inside. And so let me just jot this over here. If I have like x plus 2, and I say, oh, I'm going to square that, it is not okay to say, okay, x squared is x squared and 2 squared is 4. This does not equal x squared plus 4, right? However, since everything is being multiplied in here, I can just distribute this 3 to each one of these exponents. And that's, in fact, what I'm going to do. So, real quick, for the thing I just did over here on the right, what you'll have to do is you'll have to say, this is the same thing as x plus 2, because multiplied by itself exactly this many times, x plus 2, right? And then you're going to have to distribute that, FOIL it out, and get an answer. I'm not going to do that here. That's in a later video. But if I do the same thing here, you know, I could say, like, well, not the negative 3, but for the third one, I could say, oh, this is the same thing as x squared times y times z cubed times, and then multiplied by itself 3 times, and so I work it out. And it's going to be the same thing as if I just distribute this 3, because there's no pluses or minuses kind of breaking it all up in the center. All right, so if I distribute that negative 3, I have x, because again, if I have, just to reiterate, if I have a squared and I raise that to another power, I multiply these two, right? So I have 2 times negative 3, so I have x to the negative 6 times y to the 3 times negative 3, that's negative 9. And then again, if you put the z as a 1, z to the 0 as 1, then you're done. If you didn't, I could say, oh, z to the 0 times negative 3, well, 0 times negative 3 is still 0, so I'd have z to the 0. And again, it'd still be 0 to the 0 is 1, so I'm not even going to write that down. You could put times 1, but at whatever point, you can keep carrying z to the 0 through if you really want to, but it kind of gets just kind of in the way, but it will work out if you just keep carrying it through. In the second term, so I have this times, and then I have 2 x squared times the positive 3, so that's x to the 6. And then I have a 1 times 3, that's y to the 3. And then I have a z to the 3 times 3, that's z to the 9. And then you don't have to do this step, but I'm going to do it just so it's kind of more clear. I'm going to rewrite this as x to the negative 6 times x to the 6. I'm going to put all the letters next to each other. Y to the times y to the negative 9 times y to the positive 3. And then times, if you have your z to 0, you can put in the z to 0 here if you'd like to. And then times z to the 9th. And now, again, with the whole a squared times a cubed, you add the exponents together. That works whether it's a's or x's or y's or z's or q's or 5's. And so I could do that here, I could do that here, and if you have the z to the 0 still, you can have that there. 9 plus 0 is still 9. And so when I add this x to the negative 6 plus x to the 6, then I have x to the 0, and x to the 0, that's just being 1. So really these cancel each other out, right? And or you could think of it as, this is x to the negative 6 here, so I could rewrite that as 1 over x to the positive 6. And then I would have x to the positive 6 over x to the positive 6, which is also 1. Any way you slice it, the x's are going to cancel out, and they're going to be 1s. I have a y to the negative 9 plus 3, so negative 9 plus 3 says y to the negative 6, and then times, and again, if you have the 0 there, you can work that out, but z to the 9th. So my answer would be y to the negative 6 times z to the 9th, and again, typically in upper division mathematics, that's perfectly okay. But for this test, for the study guide, and really a lot of algebra and lower calculus, you do want to rewrite this with positive exponents. So I could rewrite that and say this is the same thing as z to the 9th over y to the 6th. And that's what our answer is, our final answer in the back of the book. And that's what it would be as an option for A, B, C, or D. You're not going to see this. Even though it's the same kind of, it would be the same, it's correct, it's the same answer, you're not going to see that. You're going to see the one on the right, the one that's boxed off. Okay, so moving on, that's number 3. So moving on to number 5. Let's see, number 5, we have, let's see, in parentheses, and these are brackets, and brackets we can treat like parentheses unless you're talking about intervals and stuff, but q to the 3rd power over p, and these p's and q's are looking similar, so make sure you have the correct letters in the correct spots, plus r over q, and then we're multiplying that by p, there's a lot of letters in here, q squared r cubed over r squared. Okay, so where do we start? Well, so you can, with this problem, start in a lot of different places, but I'm just going to start over on the left and kind of work my way through. And just like, just real quick again, if I have a, and I let's say over b, right? And we'll say a squared, and we'll say b cubed, and I raise that to the, let's say, 3rd power. Just like I said, you distribute that to that. You also distribute it down here to this. And so in this first term over here, I take that 4, the exponent, and I distribute it down to each of those, and that p I can say is p to the 1. And so this term turns into q to the 3 times 4 is 12 over p to the 4. Okay, and then the first thing I'm going to do is here is I'm going to leave this fraction r over q alone, and I'm going to say multiply that by, and then I'm going to distribute this 2 everywhere, right? I'm going to this squaring everywhere, and so I have p to the 1 times 2, so that's p to p squared, q to the 4th, r to the 6th over r, and then 1 times 2 is so squared, and that gets rid of our exponent. And now what I really have is 2, fractions. I have a fraction over here and a fraction over here. But before I start trying to find a common denominator, I'm going to actually cancel out terms that and simplify a little bit. And so I can cancel out this r squared with this r to the 6th. So this becomes 6 minus the 2 so this is r to the 4th. I have a q down here, that's a q to the 1, and a q to the 4 up here, so I can say that's q to the 3. And then I have another r over here, and so I'm going to add that to the 4. And so what I get after all of that, this term is still the same, q to the 12th over p to the 4th, plus, and then I have a fraction here, but the fraction, since I canceled these out, the fraction, well, that's just the 1 on the bottom. And then I have a p squared. The q was whittled down to a 3, and then the r to the 6th, if I add the other r that's out here, I have a, it's not plus or minus, it's timesing r to the 5th power. And that, I put it over 1 just so we can kind of see what all happened, but really I should leave it as over 1 because I'm going to have to do that anyway because I'm going to have to find a common denominator. And I would have this stuff as a whole number, you might say, but when I have to add it to this fraction over here, I have to put it over 1 so that I can have a common denominator. And our common denominator, it's nice that it's a 1 because our common denominator can then just be p to the 4th. Common denominators with variables, again, typically you're just going to multiply them by each other, as we'll see in problem number 7. But since this is just a 1, I kind of am multiplying them by each other. But I'm multiplying the top also by p to the 4th, so that if I look at just this right here, p to the 4th by p to the 4th is just 1, and 1 times anything is just itself. So I'm not really changing anything by multiplying top and bottom by p to the 4th. So this becomes, again, the left-hand term doesn't change at all, and so that's q to the 12th over p to the 4th plus, and then I'm multiplying this p to the 4th through, and since I have p squared already, that becomes p to the 6th, q cubed, r to the 5th, all over p to the 4th. And then now that I have a common denominator, I can simplify it and just combine it over to common denominator. So I would have q to the 12th plus p to the 6th q cubed r to the 5th all over the p to the 4th common denominator. And honestly, that's the final answer. That's correct, right? However, if you look at the back of the book, and honestly, since the back of the book is doing it, the back of the study guide, I hesitate to say that the test won't do this. So I'm going to show you what happened. But and this is a good example of, oh, I got my answer, but it doesn't match any of the possible choices. And so can I manipulate my answer to look like one of the possible choices? And so if we talk about distribution and factoring, if I look at the top, I can see that there's q's in both of those, right? And so I can factor out something. And in fact, I can factor out a q to the 3rd power. And if I factor out a q to the 3rd power, then what I have left in the first term would be q to the 12th divided by q to the 3rd power. I have q to the 9th plus, and then q to the 3rd divided by q to the 3rd, so that becomes a 1. So I just have p to the 6th, r to the 5th. And this is all over p to the 4th. However, I said earlier that the only reason that you would factor something out, there's two reasons, and one of them is to help you simplify, and the other reason, as we might see in one of the last videos, is to maybe solve for something like a quadratic equation. And factoring out a q cubed here actually serves no purpose, so I'm not really sure why they did it. I don't like it. I like our left side answer here. But again, if you get the left side answer here, and that doesn't match any of the choices, and in fact the right side is an option, then that's when you have to ask yourself, can I make my answer look like one of these answers? Again, I don't know why they did that. I don't like it, but they did it, and it is what it is. So that's how you pull out a q cubed, and it looks like that answer. And honestly, when you're in class, there are times when your answer is not going to match the back of the book, and your professor's going to be okay with that because maybe they simplified it a different way, or they did something different, but your answer is still correct. And so don't sweat too much in class. Now don't get me wrong, like if I would definitely ask about it, your professor, if it's a different answer, because maybe it's not the same thing. But if you get an answer and it's the same in the back of the book, not the same, but a different answer in the back of the book, and you plug a number in, like for your variables, and you end up getting the same, like with using a calculator, same decimal perhaps as the answer in the back of the book, well then obviously yours are the same. And maybe there's a reason why they simplified it. Maybe they simplified it more, or a different way. Maybe there's a reason for that, but that's definitely a question to ask your professor, whether what way he likes it. But I've been in a lot of situations where my answer didn't match the back of the book, but it was still correct, and my professor accepted that. In this case, I'm not sure really. I don't see a reason why they did that, but there it is. Moving on to the last problem that we're going to do in this video, number 7. Again, I'm doing the odd problems, but I'm not going to do 9 and 10. As I explained earlier, if you like to go back to 9 and 10, I'm still not going to do it in this video, but I would suggest, if you're not familiar with that, watching the later video on factoring, getting familiar with that, and then trying 9 and 10. But moving on to number 7, we have, let's see here, we have 3 over x, this one's going to be fun, not 3 over x, I'm sorry, 3x over y, make sure you write it down correctly, plus 1 over 2x, plus 2 over xy squared. And so if you're not comfortable with fractions to begin with, this might not look fun, but because there's 3 terms, but there's a bunch of variables in the denominator. So here's how we deal with that. I take my first denominator, and so there's no way, there's no way, but I'm not even like think about a least common denominator. I'm just gonna, and I'm not gonna just, well, I am. Let me just think what I'm trying to say. I'm not gonna multiply all the denominators by each other, but I'm also not gonna, take time to kind of, well, how can I make this the least common denominator? Instead, I'm gonna look at my first term, and I'm gonna ask myself, what am I missing from this first term? That this second term has in its denominator, right? And I'm going to multiply it by that. And so I don't have a 2, so I'm going to multiply by 2. And I don't have an x, so I'm going to multiply by x. And then I don't, and then go to the third term and say, well, what am I missing to make this first term's denominator look like that? What does that third term's denominator have that I don't? And so, you know, it has a 1 and I have a 2, but so that doesn't matter because I'm looking at what they have that I don't. They have an x. Well, I have an x now because I've already multiplied that. I have an x, so I don't have to worry about that. They have a y squared, and I only have a y, so I need to multiply this by y. And then that's your common denominator, right? Y times 2 times x, right? And I'm just going to write that over there. Y times y is y squared times 2 times x, so 2xy squared. So that should be my common denominator. And then I go to the second term and I say, okay, well, I'm going to look at that first term and say, well, what is that first term now? Because that's the only one I care to look at now, because that is what my common denominator is. But what do they have that I don't? And so this second term is missing a y squared because it's missing 2 y's. And so I'm going to put that in there. And then what is this third term missing that first term has? And it's in fact missing just the 2. So I'm going to multiply this one by 2. And then I got to go back through and I got to say, well, whatever I multiplied the bottom by, I have to multiply the top. So I'm going to multiply it by y and by 2x for that first term. I multiplied the bottom here in the second term by y squared, so I got to multiply the top by y squared. And I multiplied the bottom on the third term by just a 2, so I got to multiply the top by a 2, not a 4. That's what it will become. So times 2. And then I'm going to kind of do the math, right? And so for my first term, I have y times 3 times x times 2x, and that becomes 3. Oh, I'm not 3. 3 times 2 is 6. So 6, x times x is x squared, 6x squared y. And this is over our common denominator that I put over here. So that's 2xy squared. And then plus, on the second term, well, that's easy now because that's just a 1. So 1 times y squared, that's y squared. And that's over the common denominator, 2xy squared. Plus, and then the top over here, that's easy. That's 4 over 2xy squared. And then now that we have the common denominator of 2xy squared, I can just combine everything and I have 6x squared y plus y squared plus 4 all over 2xy squared. And that's the answer. There are times when perhaps you could simplify the top and say I have a 4 right here, and maybe another place I had like a 6, so I can, just the numbers, right? I can't combine the 6xy squared with the 4, but if it were just a 6, I could combine those. So sometimes you can simplify the top, sometimes you can't. But if you could, that would be another step, and you would do that. In this instance, we can't. And after checking the back of the book, this is, I don't know, maybe they factored out something weird, which you can, but I don't know. But this is the answer that they have in the back of the book. So that's our final answer. I would definitely practice that one if you're not feeling comfortable with that one. Also, one that's kind of similar as far as fractions stuff go. Number 6. So I would try number 6, but definitely with 3 terms in 3 fractions, different variables and stuff like that. This is definitely probably one of the harder fraction ones you're going to see. So you want to get comfortable with that. And then, like I said, I'm not going to be doing number 9 or number 10. If you want to try those, if you're comfortable with factoring, by all means, they're fun problems. But try them out, and if not, come into the Junior Center and see us.